Alright everybody, here we are and I hope I'm audible right now, and let's just simply get started. As long as I have my battery is not dead yet, I mean is not dead, and till then we can just simply keep going on, and once it's over then of course I'll have to end the stream. So today we are mainly gonna be covering this particular section, like how can we actually build our own database, and again this is something that I have to revise, and of course that's what we are doing here in this live stream, so we are gonna be getting these things done. On your end? Yeah. So one more thing, that is as for the screen, I'm actually gonna be sharing on this one. Okay, seems good. Coming back to this one, so we are gonna be just simply summarizing everything over here, and hopefully it's gonna be fine. Collapse this. Yeah, going ahead from here, what is the thing that we have to talk about? That is how to build our database. Exactly what all problems we are gonna be facing while building this and all. So Notion. Just a sec, give me a moment. Let me open that particular section here. That was 16th one, and we see not this one. So in that case, 15th. Yeah, let's design a database. Coming back to this, there is something called RDBMS, like Relational Database Management System, and we will try to design sort of that database, that type of database only. By the way, when it comes to the requirements over here, so we have a few requirements that our data should be fast. There should be fast reads in our database. We should be able to get the queries done really quickly. Then we have writes, more important, like even writes should be fast. So ultimately when it comes to reading and writing, they should be fast. Durability, it should be durable, and durable in the sense it should be it shouldn't be going down every now and then and all. Unstructured data, that simply means we should be able to save some kind of unstructured data as well. And lastly, handle a few petabyte actually. So petabyte means 10 to the power 15. So this much 10 to the power 15 bytes data. So this much it should actually be able to handle. By the way, when it comes to RDBMS, so in RDBMS we have a schema predefined, and for every row we know the exact size and data type. So the thing is that what we want over here, that in our case the database that we are trying to create, alrighty, there are few requirements, that it should support fast reads, it should support fast writes, it should be durable. Okay, it should support unstructured data. And lastly, what was the last thing? Yeah, it should be able to handle few megabytes of data. So this is nothing but the requirement, able to handle few megabytes of data. So these are the requirements right now, and especially when it comes to RDBMS. So let's just simply have everything here. So RDBMS, Relational Database Management System. So when it comes to this, so what exactly happens here, that it has fixed columns, right? So it has fixed columns. When it comes to these fixed columns, means those columns have fixed sizes, right? So at that time it's easy to simply it's easy to determine the kind of the size of that particular column. Hence we will be able to calculate the overall database storage that we need. But in case of unstructured, that's not guaranteed, so we'll just simply have a look at that. So ultimately, suppose we are using RDMS database, so we are gonna have probably some columns. If one of the columns is ID, then another one is name, price, rating. This is how we have the columns. So the first one is gonna be the primary key for sure, and they'll have the data in the bytes. Just a minute. Now how will this be structured data stored on SSD? Now what will happen during the reads? Assuming the data is ordered by ID, because of fixed schema and defined size, the DB knows exactly where the next record is. That is right. Just a minute. Assuming the data is ordered by ID because of fixed schema and defined size, the DB knows exactly where the next record is. Why? Because from starting byte of one row, we can add 84 bytes and reach the next one. So on the hard disk, if we are storing it like this, yeah, that's fine. Even for update on a specific column of a row, we just need to go to specific location and update. Because updates won't even change size of data, hence allocated memory space will be the same. Now can we try to think of a key value based NoSQL database, how data on a hard disk will look like? Alrighty, it makes sense anyway. Alrighty, I was just simply going through my notes anyway. So the first thing is that the data should be durable, and when it comes to RDBMS ultimately database, so it has fixed columns, and those fixed columns, they have their fixed sizes. So if we actually talk about RDBMS database, so that suppose we have the ID, and then we have name, we have what all do we have? We have ID, we have name, we have price and rating. These are the things that we have. Now we have to just simply assume the type size of them. So ID, price, rating, they are gonna be numbers. So if there is any number, so usually what is the size of a number? If there's any number, suppose okay, 1 or something. So one integer is of 1 byte, size of an integer in JS. So JavaScript stores all numeric values as a 64-bit floating point, meaning there is no distinct integer data types separated from floats. Maximum safer range, the largest integer that it can store is this. Minimum can be this. Precision, okay. Isn't there any specific size for this? Not JavaScript actually. Int size in SQL. So for different storage requirements, SQL offers these integer variants. We have tiny int, small int, big int and all. Tiny int is 1 byte, 0 to 255. Small int is from minus this to this, and big ints are from this to this. So ultimately big ints are gonna be there right all the time. That simply means 8 bytes. Yeah, makes sense. So and apart from this, we are gonna be having names, and we are just simply gonna be assuming over here, as simple as that. Okay, coming back to this. Oh yeah, this is the only thing that's visible right now. Yeah. So ultimately, if we have over here, if we have a number, like we have the ID, so if we are using big int, because we never know how much the data is gonna be, so of course we are gonna be using big int. Hence it's gonna be of 8 bytes, and the name ultimately how many characters can it have. So if there's any name, so one character is almost of 2 bytes, and if we just assume that a char can have max 30 characters, so it will have almost 60 bytes, just like this. Again, this is nothing but the assumption over here, but overall this is how we are gonna be going ahead. So name will have 60 bytes for just it can be even more or less, it depends, but we are just simply assuming it over here. Price, it will definitely have 8 bytes only, and as for the rating, it will also have 8 bytes rating. So this is how we just simply go ahead. Alrighty, now the question is, suppose this has this much rating, this much space, right? It needs this much space. Total, if we calculate, that's gonna be 8 3 24, so ultimately 84. So the total is gonna be 84 bytes it needs. So now the question is that how we are gonna be querying the data. So when it comes to querying the data, first of all, it has fixed size. So if we store it on HDD hard disk ultimately, so this is the hard disk suppose we have, and we store this particular section over there, and hopefully we are gonna be able to, yeah, that is even better. So but that's not that good either. Yeah. Alrighty, this is what the hell, what have I done? Yeah, this seems to be better. So suppose this is the data that we are actually storing inside HDD hard disk. So ultimately this is nothing but hard disk, and we are storing this data. So whenever we are querying the data, we already know the starting value, and we know how many columns are there, and we know even the size of those columns. So if we are querying, so we'll start from the beginning, and if we just simply sort of sort the ID. So if the ID is this is the size of the IDs and all. So the next thing that we have, this is not the value, or rather the sizes. So these are the sizes here. So suppose if we start looking for a particular document using the ID, because the ID is always gonna be the sorted one, so we will be able to check. So if the ID is first, so we'll query the first one. If the ID is second, so suppose this is the first data that we have in the hard disk. This is the second one, this is the third one, this is the fourth one, and this way we have many. So what will actually happen, that if the ID is 1, we will get the data from here. If the ID is 2, so we will just simply add so whatever the reference point of this is. So suppose it starts at 00 byte, and it just simply goes till 84 bytes. I mean, hopefully this is how it just simply stored. So if on HDD, because we talk about storage here, so ultimately it is nothing but ultimately what it is, a storage where we can store some data, and at the end of the day, that data is gonna be stored in bytes. Suppose 84 bytes got stored here, right? So 84 bytes got stored here, and after 84 bytes, the remaining 84s are gonna be stored here, then they are gonna be stored here, and lastly remaining 84s, they are gonna be stored here, and similarly it will just simply keep going on. So suppose the ID is first, so we will get the first 84 bytes. If the ID is second, we will get the second 84 bytes, and to calculate that, we already know that it has fixed size as well as fixed columns. So when we want the second 84 bytes, so we will just simply add, suppose starting was 0 byte, so we went from 0 to 84 bytes. That was the data for the first one. Then we'll add 84 plus we'll start from 84 bytes, and we'll go till what, probably 84, 160, 168 bytes. So the data from 168 bytes to 84 bytes, that belongs to this second one. Similarly, if we want third one, so we will add 84 to the bytes. That simply means whatever we get from there on, that's gonna be the third one. Similarly, we'll keep adding. So ultimately, as they have the fixed size, like it's always gonna take only 84 bytes. That simply means after that, whatever comes, that's the next data. Then after that, the another one is the next data, then the next data, and this is how we just simply keep going on. I hope it does make sense. Anyway, they add this code section over here. I don't know how this is added. I'll see, because I'm also working on one of the clones of the board, so we'll see exactly how it goes. Even this is not bad, having these things here. Okay, never mind, coming back to this. So this is what we've done. So ultimately it is sort of fixed, and so because from starting byte of one row, we can add 84 bytes and reach the next row. That is right. Even for update on a specific column or a row, we just need to go to a specific location and update, because updates won't even change the size of data, hence allocated memories will be the same space. So ultimately, if we are talking about RDBMS data, so at the end of the day, This is gonna be the first row, this is gonna be the second row, probably I'm gonna be keeping it here third row, and this one is gonna be the fourth row. And now if I want the data, so using the ID we can get it as per getting it on the hard disk. So as the first one has 84 bytes, that simply means if I add 84 to the first one, so we are gonna be getting the second one. If we add 84 more on this, so we are gonna be third one and the fourth one, and this is how it will just simply keep going on. Now let's go through some good stuff, because it's been like RDBMS is sort of everything is predetermined over there. Now can we think of a key value based NoSQL, that simply means unstructured database, and how data on HHD will look like. Usually when it comes to RDBMS, so data sort of looks like this, that data is actually stored on HHD, and especially when it comes to hard disks, there are few things here, like there are sectors on hard disk storage, hard disk storage. Just a minute. Images. Not this, hard disk storage. Internals. Block, sectors, etc. Alright, here we are. So this is how I hope I'm gonna be able to see something good. Ultimately this is how the hard disk looks like. So coming back to internally, ultimately this is how the data is actually stored. Coming back to this one, there are three things. There is a track, so this whole thing is a track, one circular section. Then we have sectors as well. So disk sector we have. This is sort of a block ultimately. So track sector is nothing but a block. This whole circular thing is a track, and this disk sector is a perpendicular section that just simply goes from top to bottom. And coming back to this, if the data is actually stored in a block or the track sector, then the data can easily be accessible, because whenever we need to make a query, so the query will go, operating system will just directly get the data from the block, and it will be able to give you the data. But if the data, some data is stored on this block, some data is stored on this block, then operating system will actually have to just simply fetch the data from here and from here, and that's gonna be a bit time taking. Hence, if that is in the same block, that's gonna be sort of a bit quicker. Apart from this particular thing, when it comes to RDBMS, so we'll even see. But before that, if I can find some good images, let's skip this section today only. Today we'll exactly see how the data is actually stored, how SQL stores data. I'd better look for some top ones here. We'll see which article is good, and we'll just simply be going through that really quickly. I think this much should be enough anyway. Coming back to this, what is this? How is data stored physically in database SQL server in English? Just this much. It's just the beginning, bro. Thank you so much for sharing this one. As I do. Okay. The language is different. Coming back to this one. Alrighty, this is gonna be useful too. How about this? I don't read something that is too verbose, and in case of this one, it is actually so I'd like to skip this. Alrighty, so these are the ones that I've selected here. Let's close everything. Come on, yeah, I should have had that. Here, coming back to this, let's simply go through this particular article really quickly and then we'll see. So have you ever wondered how SQL physically stores a table data internally? Well, data in tables is stored in row and column format at a logical level, but physically it stores data in something called data pages. Okay, a fundamental unit of data storage in SQL server is the page. Wow, so this is page is nothing but the fundamental data storage unit. So the fundamental unit of the data storage in SQL, that is page. The extent is a collection of 8 physically contiguous pages. The extent so is a collection of 8 physically contiguous pages. So ultimately 8 pages which are side by side, like near to each other. The collection of those 8 makes the extent. In a regular book, all content is written on pages. So in a regular book, all content is written on pages. So that is right. Similar to book, SQL Server writes all data rows on a page. So all data rows on a page. So one row is just on a page. So all data pages are the same size, 8 KB. So all data pages are the same size. So ultimately the fundamental unit is page, first of all this. And apart from this particular thing, when it comes to SQL here, it's better to just simply go through it. I mean, why not? I have enough time. So when it comes to SQL over here, so first of all, it has a few things over here. First one is the fundamental unit and storage unit, of course, storage unit, and that's gonna be the page, and the page size of page that's gonna be 8 KB. Come on, can't I type well today? So this is how we just simply go ahead. So okay, let's continue to the next one. What is the next thing? So similar to a book, SQL Server writes all data rows on a page. Okay, all data pages are the same as 8 KB. Extents are the basic unit in which space is managed. So extent is nothing but the unit where the space is managed. And at the end of the day, extent is a collection of 8 physically continuous pages. So ultimately when we talk about extent over here, so this is the first thing. Then there is something called 8 contiguous pages, that's gonna be making extent. So this is how it just simply goes on. And going ahead to the next section, extent are the basic unit in which space is managed. So ultimately sort of extent manages the pages. Ultimately it is just a collection of pages and all. An extent is 8 physically contiguous pages. That simply means around 64 KB. That makes sense. So when it comes to this, because it has 8, so 8 is the 64. So ultimately the size of this is gonna be 64 KB, just like this. So this is done as well. What's the next thing here? The next thing is that so this means that SQL Server database have 16 into 64. That simply means 1024. That simply means 1 MB. So 16 extents per MB. So if we want to know how many extents are there in 1 MB, so we'll just simply divide 1 MB, that simply means this with the 10 to the power with the 64, and if we divide it we are gonna be getting 16. So 16 extents are around 16 extent, because if we just simply say that 16 multiplied by 64, we are gonna be getting 1024. Yeah, that's right. So we are getting that, so that makes sense as well. So we are gonna be getting 16 extents in 1 MB. That's simple. Let's move to the next one. So what's gonna be there? One extent is gonna have 8 pages. Total size is gonna be 64 KB. So this is these are the pages 1, 2, 3, 4, 5, 6, 7, 8. 8 pages are there. This is the overall one extent, and the table in SQL Server is actually stored in a tree-like structure. So let's understand this in a simple example and all. But ultimately, this is one extent here. So let's just simply copy the image, and if it is possible, let's just simply place the image here. Alrighty, makes sense. Going to the next one. Here we are. Create table employee ID, employee name, and employee position. Suppose this is the table that's actually being created. So the first one is going to be the primary key. The last two are the strings varchar 50. That's the size they have. So employee ID is the primary column key. That's right. So by default, a clustered index on this employee ID column is created. So by default, a clustered index on this employee ID column is created. So if that is a primary key, it will automatically be indexed. This means the data that is physically stored in the database is sorted by employee ID column name. That makes sense. Let's go here. Select everything from employee. So this is how the data is actually stored. And similarly, we'll have 4000 rows down the line. Okay. Did I click on something? Yeah, I did. Yeah, for example, let's say we want to have employee with 4000 rows. So the first one is gonna be one that's gonna have, what is this, employee ID and all this. So we have one. Let's say we want to have employee with 4000 rows. So root 1 2000 to 1, then 1 1000 to 1, it's going completely over my head. The nodes that you see at the bottom of the tree are called data pages or leaf. So these are the data pages, leaf. So we have 1000, we have 1 1001 2001 3001, and what kind of, okay, or data pages or leaf nodes of the tree, and it is these leaf nodes that contain our table data. So ultimately they contain the table data. Okay, fine. The size of each page is 8 KB. This means the number of rows that are stored in each data page really depends on the size of each row. So the size of each page is 8 KB. So one page only has the size of 8 KB. This means the number of rows that are stored in each page, data page, really depends on the size of the row. So if the size is bigger, so it may be using multiple pages and all. For our example, let's say in this employee table we have 4000 rows, and let's assume the table size is 80 KB. That's what we assumed earlier. So 80 KB. So one table, that simply means including these three, so they are around 80 KB and all. So sort of fine. So this table will be stored in 10 pages, because one page can only take 8 KB of data. So if we want to store this whole table, whole row, so this will be stored on 8 pages or 10 pages. So we have 4000 rows. Let's say assume the table size is 8 KB. That simply means one row, hence that's gonna be stored in 10 pages. So 10 pages, one extended plus 2 pages. So 10 pages means what? 10 pages means one extended plus 2 pages. That's right. So ultimately, if a table size is ultimately row size, whatever you call that, so coming back to this table size, that's gonna be, if we have 80 KB in our case, that simply means how can I keep it in words here? So if we want to store 10 pages, that makes sense. So coming back to this one, if I want to store 10 pages, so 10 pages means how much? 80 KB. Table size 80 KB, that is right. So that simply means we need 10 pages. 80 KB means 10 pages, and 10 pages means one extender plus 2 pages. This is how it just simply goes on, and this is how we are gonna decide what is needed and when. So ultimately, if the table size is in our case, suppose we are assuming that we have these values here, we have ID, name, price, and rating in all. In our case it was 84, in his case it is 80 KB, that is completely fine, so that the calculation is simpler. On the basis of that, if the size of the one row is this much, hence if we try to see exactly how many pages can store this much data, so one page can store 8 KB data, so 10 pages can store 80 KB data. That simply means, and one extent is equivalent to 8 pages, so that's gonna be one extent plus 2 pages. I can even make it better. 8 pages plus 2 pages, and if I even go further, that's gonna be equivalent to that's going to be equal to what? One extent plus 2 pages. So this is how it's actually gonna be going on. I mean, it does make sense anyway. Alrighty, what is the next thing that we have to go through? So this is all about how the data is actually getting stored, right? Remember, the important point to keep in mind is the rows in these data pages are stored by employee ID column, because employee ID is the primary key of our table, hence the clustered key. That's right, sort of indexed one. The node at the top of the tree is called a root node, and the node between the node and the leaf nodes are called intermediate leaves. The root and the intermediate level nodes contain index rows. So ultimately they are gonna contain index rows. So root and intermediate, because the ID is gonna be the primary key, and that's gonna be the clustered ID ultimately. So this one, and that's gonna be clustered. So by default, a clustered index on this employee ID column is created. So that's gonna be indexed, and that's gonna be the cluster indexage, and that's stored on the first and second nodes or leaves, mainly nodes, root and intermediate, and then we have the third node, that's gonna be the leaf. The leaf nodes contain the actual data rows. The root and the intermediate level nodes contain index rows. Okay. So ultimately, if there is a, even we have to make sure that it does contain that, right? Okay, this is here. So ultimately, when it comes to this, so we have clustered indexage. So we have clustered indexes, and they're actually gonna be sort of here. So let's keep it here. Apart from this clustered indexage, we'll actually have the data, and that data itself is gonna be somewhere here. So the data is gonna be here. As for the clustered indexes, they are gonna be either on this, okay. Can I change the color of it? Such a bad thing this is, but okay, never mind. This is how it just simply goes. Cluster indexes, they are actually gonna be here, and it's sort of Okay, that's fine. It's gonna be here as for the data that's actually gonna be stored here. This is not gonna be here, that's actually gonna be data. So data is actually gonna be stored here. Going ahead, what's the next thing? So how SQL Server finds a row by employee ID. So for example, let's say we want to find a row with the employee ID 3501. So 3501, that's not even here. So select everything from student where the student ID is 3501. So find 3501. So we have first step, this we look for it here, then second step look for it here, the third step look for the data. So the database engine starts at the root node and picks the index node on the right, index node on the right. Okay, because the database engine knows this node contains employee ID from 2001 to 4000, 2001 to 4000, 2001. It will send it on the right side. So from there it picks the leaf node that is present on the extreme right, because employee data rows from 3001 to 4000 are present on this leaf node. So this is the like it starts at 2001. Everything less than 2001 is on the left side. So like 1001 and all, and everything greater than 2001 is on the right side. When it comes to 1001, so everything less than that is on the left side, everything greater is on the right side, and this way just simply calculated. So on the left side lesser values, lesser indexes come, on the right side greater indexes come, and that's nothing but a range. That is it. From there it picks the leaf node that is present on the extreme right, because the employee data rows from 3001 to 4000 are present on this leaf node. The data rows in the leaf node are stored by employee ID, so it's easy for the database engine to find the employee row by this. Wow, finally I hope this article answers any questions you might have had. I think it does make sense. So ultimately what is happens that everything starts at the root level, and then we have the intermediate level, and at the end we have the leaf level. The leaf level is the level that actually contains the data, and apart from this particular thing we have this. So this is the root level, and it has the ID suppose 2001. That's the range, and from here if some less than 2001 comes here, so it has intermediate leaf. Intermediate leaf means intermediate leaf has the data between 1001 to 2001, and the second one has 2001 to 3001. So this is the range, so it gives us the range, even this is giving us the range. Now once we got the range, that okay, from 1 to 1001 we have the data here. So like it's pretty simple. This is initially we had the data from 1 to 2001 on the root 1. Okay, the data range was this. Now that on the left side I got the range from 1 to 1001, and on the right side 2000 to 2001 to 3001, and the middle one has the range between 1001 to 2001, just like this. Then similarly it's further divided into 1 to 1001, then from 1001 to 2000, then 2001 to 3000, and then 3001 to 4000. And this is how the range is actually being calculated. Once the range is actually calculated, so if we have 3501, in that case we'll come here, we'll see whether 35 is greater than 2000, is greater than this range or not. It is greater than this range, hence I'm gonna be sent here. Then I'll see if this is greater than this range or not. It is still greater than that, so I'll actually come here, and we'll see if it is greater than this range or not. This is not greater than this range, hence I'll start looking for the data in this particular page or extent, whatever you call that. This is actually the leaf, so we'll start looking for the data, and it is the combination of pages or extents and all. And at the end of the day, because the data is structured, we know the ID and all, ID is clustered, we'll be able to find the data. Let's go through it one more time. I mean, yeah, it does make sense. But so have you ever wondered how SQL server physically stores table data internally? Well, the data in tables is stored in row and column format at the logical level. but physically it stores data in something called data pages. Okay, that's fine. They're not just the pages, they are actually the data pages that we just simply wrote here. So when it comes to this particular section, so the fundamental unit store is the data page. Okay, coming back to this. Yeah. So the fundamental unit of the data storage in SQL Server is the page. The extent is a collection of 8 physically contiguous pages. In a regular book, all content is written on the page. So this is just an example. On pages, similar to book, SQL Server writes all data rows on pages. That's fine. And all data pages are the same size, 8 KB. Extents are the basic unit in which space is actually managed. So an extent is 8 physically contiguous pages, that simply means 64 bytes. This means in 1 MB we have 16 pages, and 16 pages means not really this. One extent means 64 KB, right? So in 1 MB we have 16 extents at the end of the day. Yeah, we have 16 extents in 1 MB. One extent 8 pages. One page has 64 KB. So one page has 8 KB. So the total size is gonna be 64 KB. The table data in SQL Server is actually stored in tree-like structure. Let's understand this with a simple example. Consider following employee table. So ultimately this is the ID and these are the names and all. So it will have some space, it will take some bytes, and it will take some bytes, it will take some bytes. At the end the total is gonna be 80 bytes around. That's what's mentioned here. Employee ID is the primary key column, so by default a clustered index on this employee ID column is created. This means the data is physically stored on the database. Come on here, how much am I gonna sneeze? Anyway, excuse me for that. So this means the data is physically stored in the database, is sorted by employee ID column. That makes sense. So select everything from this. So this is how the data is actually stored. For example, let's say we want to have a employee with 4,000 rows. So how are we gonna be storing employees with 4,000 rows? So for that thing we are gonna have leaf, and we'll make sure that we have a range like 1 to 1,000, 1,000, 1 to 2,000, then this and then this. And first of all we have to make this range, and then we have to just simply sort of it is kind of a binary search if I'm not wrong. Like the user comes here, the user checks whether the range is the binary search or there's something. I'm not that good at the essay, but okay, there is a search called that, like that. So coming back to this one, so we it checks the ID. It starts with from 1,000 to 1,001. Less than that will come here, greater than that will go here. Coming back to this one, it is from 1,001 to 1,000, and remaining things come in between, and then 2,001 to 3,001, and now it will just simply keep going on. Similarly, it will even have many. So this is how the just simply range is decided. The nodes that you see at the bottom of the tree are called data pages or leaf nodes. So they are the data pages. So 1, 2, 3, 4, they are the data pages. There can be many data pages or the leaf nodes of the tree, and it is these leaf nodes that contain all table data. That is fine. So they are data pages, it's not like they are the only ones. The size of each page is 8 KB, so the size of each page is going to be 8 KB, and that is where we will store the data based on the ID. But if in our case the data actually is of 80 KB, that simply means we need 10 pages here to just simply store the data. Okay, this means the number of rows that are stored in each page really depends on the size of each row. So if we are storing any row, that doesn't mean that row is gonna be fully stored on the same page. If the data size is 80 KB, it will be using 10 pages. Okay, the size of each, okay fine, that's gone. For example, let's say in this employee table we have 4,000 rows, and let's assume the table size is 80 KB. table size is 80 KB, so the table will be stored in 10 pages. So these pages that we have over here, it will be just using 10 of them, but the id is sort of, what about the id range? 10 pages, one extended 10 pages. Remember, the important point to keep in mind is the rows in these data pages are sorted by employee id column, because employee id is the primary key of our table and hence the clustered key. So this is the range, and on this range only it's gonna be stored. But there can be many pages, right? So between 1 to 1000 there can be many pages, if I'm not wrong. So this is the overall leaf, and there will be many pages inside that. So the node at the top is the tree is called the root node. The node between the node and the leaf nodes are called intermediate levels. The root and the intermediate level nodes contain index rows. Okay, that's fine. So they just simply contain the index rows. Using them we can just simply find. The leaf nodes contain the actual data rows. So what I think that at the end of the day we are being shown these many, but at the end there are gonna be many pages here, and hence probably that we will be able to store the data. So let's have an example here. So if so the database engine starts at the root node and picks the index node on the right. It picks on the right because the database engine knows it is is this node that contains employee id from 2001 to 4000, right? So from this to this 2001 to 4000, this particular range. From there it picks the leaf node that is present on the extreme right, because the employee rows from 3001 to 4000 are present in this leaf node. The data rows in this leaf node are sorted by employee id, so it's easy for the database engine to find the right employee. Okay, okay, that's fine. Few things are still confusing. What is that? That if they are actually the pages and each page have the id, I'm not sure each page have the id or each leaf have the id, and if actually each page have the id, then that's gonna be problematic. So each page should have the range, but even then the size of each page is only 8 KB, so how will the data be stored there? I mean, these doubts are there. Coming back to this, how is data stored in database? Now we know that how the database system works and how data is retrieved from the database. It would be time to understand how data is stored in the database. Inside the database, the data is stored into where the data is stored in the, okay, fine. Inside the database, data is stored into tables. That's right. As we mentioned in previous post, the S in SQL stands for structured. This means that all the data has to be stored in a standardized manner. This is why tables have been created. Tables are the simplest object structures for data storage exist in the database. So this is how just simply come on, done. Okay, what is a field? A field is actually an attribute. What the hell? This is it tells us about SQL. That is nothing but how SQL works. It doesn't tell us. It tells us how SQL works. How data is stored in SQL. This will make even more sense if we can just simply go through it. Today we are going to take a look at how SQL database stores the data. This understanding can be really helpful in analyzing the data queries. At logical level, the data is stored in the form of rows and columns, but at the physical level, it is stored in form of data pages, which are often of defined size. In SQL, by default, the pages are 8 KB and stored in a tree-like structure called B tree, indexed B tree or clustered index structure. So these are the names anyway. So it can be B tree, it can be indexed B tree or clustered index structure. So these are just the names. Let's just simply paste it here. That's just the name. Coming back to this one, the nodes at the bottom of the B tree are called leaf nodes, storing the actual table data. Let's assume we have a student table indexed at ID column, and for the sake of simplicity, consider 100 students data, sum of for data pages of 8 KB. The student table data indexed at id column will be stored in the database as below. So we have the first student, and with the id 415, this is the index row. So what to it gets the id between 200 2001 to 4000. This is the root one, right? So ultimately range is defined over here. So from 2001 to 4000, less than that will go on the left, greater than that will go on the right, and after that this particular section is actually gonna go on the right. Then we have another 4001 to 5000, and sorry, 401 to 500, and 501 to 600. So this is again a range, because it has 415, so it will go in this particular section, and this is where it will be stored. Okay, the node, and they are the leaf nodes. That simply means they are the sort of the pages. The node at the top level of the tree is called root node, and the nodes between the root node and leaf nodes are called the intermediate level. The number of intermediate level depends on the number of data rows in the underlying table. So there can be many intermediate levels. Okay, makes sense. That will be fine in that case. The root and the intermediate nodes contain the indexes, and nodes implying it will either contain the pointer to an intermediate level page or the data row in the leaf node. This tree-like structure helps the database engine retrieve the data quickly. The above diagram also shows the path followed by the database to retrieve data when queried upon the indexed column for a specific student ID. But how about when we run a query on the non-indexed column? The engine will have to search all the data from all the data rows, which can be very inefficient. Here non-clustered indexes come into play. Unlike clustered indexes, in non-clustered indexes we have key values at the root and intermediate levels, and row locators at the bottom level. When queried on a non-clustered column, both non-clustered and clustered index work together to output the result efficiently. Alrighty, the thing is that over here we only had two intermediate levels, but there can be many intermediate levels as per the need, and that is something we have to keep in mind. Apart from this particular thing, if I'm not wrong, there can be many leaves as well. So this has the range of 1 to 1000, but there can be, this is just the id, right? So one id means one row, so hence one page cannot really contain the one row. So first of all, one thing is clear, there can be many intermediate levels. That's something good. So let's just simply close this, even if I've read this. Time to talk to the AI regarding this. Now it's enough of reading. I'd better take the help of AI in this particular case. ChatGPT. I'd better do what? ChatGPT. Login. Alrighty, here we are, and if I just simply paste it here, or let's simply say it like this, it's even no use passing this. How does SQL store data? Let's have it for a reference here. Okay, coming back to this, the image is showing B plus T structure clustered index, which is how database in MySQL, DB or SQL physically organize the data. Short answer: SQL does not store rows in a simple array or linked list. It stores rows inside pages, usually 8 KB and 16 KB blocks. So 8 KB. and those pages are organized in a B plus tree. So root, intermediate, leaf nodes, actual rows. Coming back to this one, imagine this particular thing, and id is ram, and it just keep going on. If SQL stored rows sequentially, so to find this, database might need to scan everything, that is slow. So instead it uses B plus tree. So suppose each leaf can store 1000 rows. Each leaf can store 1000 rows. So page A will have rows from 1 to 1000, page B, page C. These are the leaf nodes in your image. So 1, 2, okay. Notice the red arrows. Okay. Leaf pages are linked together, that is right. This makes the range queries fast. And where id is between this and this, the database page finds this. Okay, that's fine. The database finds page B and then follows the links. Intermediate page, instead of checking every leaf page, you can check the intermediate level of that. And the database stores navigation keys. So 1 to 1000, 2001 to 3001. These are yellow boxes in your image. They don't contain rows. The yellow boxes that we actually have, they do not contain the rows, they just simply contain the range. They only contain key plus the pointer, exactly where it goes. Okay, for example 1001 page B, 2000 CD, and then the root is the entry points 1 to 2000, meaning 1 left subtree, 2001 right subtree. When searching for id 2000 and 2500, database does check the root 1 to 2001, and 25 is greater than that, so go to the right. Check intermediate, this it is less than that, so go to the left. So ultimately go to this particular range, search inside the leaf page, only 3 pages reads. What is clustered index? In a clustered index, leaf is gonna be equals, leaf node is gonna be actual data rows. That's exactly what your image shows. So root, intermediate, leaf and rows. The data itself is stored in leaf pages. Primary key creates the clustered index automatically. What about the non-clustered index? So create index name on user's name. So ultimately key value pair. Then the leaf non-clustered indexes. So the cluster in create index and index name on user's name. So ultimately on user's name the index is actually created. Then Amit will have this ID, move on this and run this, then not full row. Then the database then uses the primary key to fetch the actual data, secondary index, primary index, cluster index, actual row. Already physical on the table is stored in pages. So page 1, page 2, root, intermediate, leaf, data and all. Each page is actually MySQL InnoDB16 SQL Server 8 KB. That's right, in SQL Server that's 8 KB, and then this the database loads only the pages it needs into memory. So because they support both fast point lookup, where the ID is this, and range queries, the linked leaf nodes make ranges scan extremely efficient. Okay, that's crazy. The thing is that by default in SQL Server the size of a page is 8 KB, and you are saying that those pages ultimately the leaves they store the data rows. So a rows can have more than first of all, the way the ID range has been defined over here, that is one page will have the range between 1 to 1000, something like that, right? So now one page having the range from 1 to 1000 means it should be able to store 1000 rows, because at the end they are the IDs, and one row has one ID. So similarly 1000 rows will have 1000 IDs. But the problem is that the size of one page is only 8 KB, and the size of row or only single row can be far higher than the size of a page. So how is this actually done? Alright, it seems to be done. Let's just simply click enter and give it. Excellent questions. You are noticing very important detail that many tutorials oversimplify. Okay, the ranges 1 to 1000 and 1001 to 2000 in the diagram are not saying a page always contains 1000 rows. They are just example key ranges. The real rule is a page stores as many rows as can fit into its size. Let's assume SQL server at KB pages. So an 8 KB page is these many bytes. That is right. Some bytes are reserved for page metadata, like page header 96 bytes and all. Okay, and so the usable space is roughly around 8000 bytes. Okay, small rows, suppose your table has like this, so row size is gonna be 4 bytes, 4 bytes, 8 bytes. I was thinking of the data in the KB. Usually the size of the row can be in bytes. Oh, literally I just missed one thing, that a page is of 8 KB. This is what I missed. I just couldn't figure out this KB section. This KB is more than byte. Ultimately 10,024, sorry, not 10,000, 1024 bytes are equivalent to 8 KB, sorry, 1 KB. Now one page is has the size of 8 KB. That simply means it can store around 8,000 bytes. That simply means around 8,000 bytes. That simply means one page can store more than one row. As simple as that. Because in our case, here size of our row, in our rows the size of row was how much? 80 KB, 80 byte ultimately. So if we have 8000 bytes, so ultimately it will be able to support 100 rows. It will be able to store, as simple as that. So yeah, it does make sense now. So ultimately when it comes to a page, so a page will have the range. That range can actually be anything. It can be 1 to 100, 1 to 1000, 1 to 10,000, depending on the size of the data, as simple as that. And how we'll know the size of the data? In SQL, the data size is already fixed. So we already know that the one row is gonna be of 80 bytes. That simply means if one row is of 80 bytes, so we'll see that one page can store how many? So one page can store 100 rows. Why? Because 100 multiplied by 80, that's gonna be 8000 bytes. That's gonna be around the size of a page. So first of all, we'll it's easy to calculate the total space that a row takes, and after that we can just simply decide the range based on the total space one row take. Got it? Makes sense. Let's assume 8 KB page is these many bytes. So some header is gonna be there. So ultimately, roughly we have this much. A small case is gonna be like this. So row size is gonna be 4 bytes, 4 bytes. Ultimately 8 bytes in ignoring overhead. So 10,000 these many rows. So the page could indeed store roughly 1000 rows. That's why diagram often use ranges like this, 1 to 1000. That's fine. Larger rows, if we have larger rows, 300 bytes. So it's gonna be around 26 rows. So the range is gonna be like this. So it's not like the page will have always 1 to 1000. It can be 1 to 10, 20, 30, 40, 50, anything. What if row is bigger than 8 KB? Yeah, that is good. If we have a row that is bigger than 8 KB, this is where it gets interesting. If we are creating something like this, the content contains 50 KB text, 50 KB text, and the row page is only 8 KB. Obviously, 50 KB is greater than 8 KB. In a single row cannot physically fit into one page. The database solves this efficiently. SQL Server uses row overflowed storage. So if variable length columns becomes too large, main page, it will have pointer to overflow page. So it will store the data in the page only. So as much it will store as much data as it's possible to just simply store in the page, and then after that it will have a overflow page, and that will it will have a reference to that particular overflow page. The row remains on the main page. Large columns are moved elsewhere. So large object, suppose like this, SQL stores page ID name pointer, so it will just simply have the pointer. So at that time the larger ones are gonna be somewhere else. So actual data is gonna be log pages somewhere else in the data. MySQL InnoDB very similar. Text this and the huge content goes overflow pages. So if something is overflowing, that will go to the overflow page. So what is actually stored in leaf pages? For clustered index leaf, ID is stored there, and this thing is stored there. The entire row is stored. If it fits, if some column is huge, then we'll just simply have a pointer over here. So suppose if age is huge, so we'll just simply have a pointer, and the larger value lives elsewhere. That simply means in offload page. Another misconception, many people think leaf is gonna page is gonna be 1 to 1000, means 1000 rows. It actually means the smallest key is 1 and the largest key is 1001. That simply means anything. Leaf 1 means 1000 in this, and it actually means smallest is this, maximum is this. That simply means it may not have 1000 rows. The page may contain 20 rows, 500 rows, 1000 rows, depending on the row size. Alrighty, so it just simply stores the range. It does not mean that how many those many elements are there or rows are there. How does SQL know where each row start? Inside every page there is something called a slot array. So we have page header, we have the rows, we have slot array. The slot array store offers offset. So 120, 188, just something like this. 0. So SQL can jump directly to rows inside the page. It just simply tells that the first one takes 120 byte, and then this, on the basis of the storage that we are looking for, the size of the storage, we can just simply get that. The key takeaway, B plus T leaf page does not store fixed number of IDs or rows. It stores as many rows as fits in the page, and 1 to 1000 in diagrams are logical key ranges, not a statement that 1000 rows are gonna be there and stored in that page. And large rows don't fit in page are split using overflow or LOB pages and accessed through the pointers. Makes sense. Coming back to this one. Here we are. So whatever we had to just simply go through, we've gone through them, and this is just the normal range, and if it overflows, so it will be just simply handled by LOB and overflow pages. Alrighty, my inverter is beeping right now. That simply means I do not have enough battery, so I'll have to just simply, what the hell, I'll have to end this live right here. Just a minute, let me just simply format it better. Unfortunately, I cannot be live anymore because of course the inverter is gonna be down very soon, and hence I should be calling it right here. Alrighty, this is it. Whatever we've gone through. So we know now how